You are driving across a bridge, maybe the Verrazzano in New York, maybe the Golden Gate, and you look up at the towers. It is a breezy day, nothing crazy, and you notice the tower seems to be swaying. Not a lot, but enough that you second guess yourself. You look again, and you are pretty sure the top of that thing just moved a foot to the left. Your stomach drops a little. You grip the wheel. You think about how much steel and concrete is up there and how it is not supposed to move, right? Here is the part that surprises people. That movement is the design working exactly as intended. The swaying you see is the bridge doing its job, absorbing the wind's energy so the roadway stays calm. For most of the history of bridge building, engineers thought the opposite. They thought a safe bridge was a stiff bridge, a rigid hunk of material that refused to bend. And that belief directly killed people. The most famous bridge collapse in American history, the Tacoma Narrows Bridge in 1940, was a textbook example of a stiff bridge that tore itself apart in a moderate breeze. The deck twisted and ripped itself to shreds because it was too rigid. So the history of modern suspension bridges is a story of learning a counterintuitive lesson. The way you keep a bridge from tearing itself apart is to make the towers spin. You build flexibility into the bones of the structure, and that flexibility absorbs the wind's energy before it can destroy the roadway. This is the story of why the towers flexing on a windy day are the safest thing you will ever see, and how engineers figured out that the best way to fight the wind is to stop fighting it. Before we get to the towers and the spinning, we have to understand exactly why a bridge deck tears itself apart in the first place. And the Tacoma Narrows Bridge is the perfect case study because it did not fail the way people think it did. The bridge opened in July 1940 in Washington state. It was a suspension bridge, a sleek and slender design that spanned the Puget Sound. At the time, it was considered state-of-the-art. It was the third longest suspension bridge in the world. The engineers followed every standard that existed at the time. They made the deck stiff, they made it heavy. They did everything the textbooks told them to do. And then, 4 months later, in November, a wind came through. It was not a hurricane. It was a steady breeze, around 40 miles per hour. And the deck started to twist. At first, it was barely noticeable. Then the twisting got worse. The roadway began to undulate, one side lifting while the other dropped, like a ribbon being shaken. Eventually, the amplitude of the twisting got so violent that the suspension cables could no longer hold the deck in its shape, and the center span tore loose. It fell into the water, and the footage of that collapse is still the most famous engineering failure ever filmed. Here is the key detail that people miss. The wind was not extreme. Bridges had survived far worse. The problem was the shape of the deck itself. The Tacoma Narrows deck was built with shallow plate girders. It was essentially a solid flat slab with a stiff edge. When the wind blew across it, the air had to flow over the top and under the bottom. And because of the shape of the girders, the air flowing over the top moved faster than the air flowing underneath. That speed difference created a lift force exactly like the wing of an airplane. The deck was acting like a wing, and the wind was generating alternating lift, first pushing the deck up on one side, then the other. Each twist of the deck changed the airflow, which made the next twist worse. The motion fed on itself. The amplitude grew and grew until the structure could not take the strain. The terrifying part is that this was not an anomaly. After the collapse, engineers across the world went back and inspected their own suspension bridges. They found the same type of oscillation beginning to develop. One of the most notable cases was the Bronx-Whitestone Bridge in New York, which had opened just a year earlier, in 1939. It was one of the most advanced suspension bridges ever built. Inspectors found that its deck was starting to develop the same rhythmic twisting that had destroyed Tacoma Narrows. The fix for the Bronx-Whitestone was to add trusses and dampers, devices that broke up the smooth airflow over the deck. They added stiffening trusses, the lattice-like structures you see under many bridge decks to disrupt the wing-like shape, and they added mechanical dampers which absorb energy. The lesson was clear. Stiffness alone does not stop oscillation, because oscillation is a matter of energy input and energy dissipation. Let me explain the physics, because it matters for everything that follows. When wind flows around a bluff body, like a bridge deck, it creates a pattern of vortices. These are little swirls of air that peel off the edges, alternating from one side and then the other. You have seen this if you have ever watched a flag flutter in the wind. The flag is not just being pushed. It is being pushed rhythmically by a train of vortices shedding off its edge. When the frequency of those vortices matches the natural frequency of the bridge structure, you get resonance. Each vortex adds a small push at exactly the moment the deck is moving in the same direction. The pushes accumulate. The amplitude grows. A deck that is very stiff has a high natural frequency. But high frequency does not mean no resonance. It just means the resonance happens at a different wind speed. The real problem is that stiffness does not remove energy from the system. It only changes the frequency at which the energy gets absorbed. Think of it like a guitar string. A tight string has a high pitch, a loose string has a low pitch, but both strings will vibrate if you pluck them at the right frequency. The tightness does not stop the vibration, it just changes the note. The only way to stop the vibration is to take energy out of the motion, to damp it. You need something that actually converts the kinetic energy of the moving deck into heat or into some other form that cannot build up. And that is where the towers come in. The tall structures that hold the main cables, the ones you see swaying on a windy day, can be designed to act as mechanical dampers. They can absorb the wind's energy before it builds into destructive oscillations. But this only works if the towers are free to move, and that was a radical idea. Early suspension bridges had towers that were rigidly connected to the deck at the top. The tower, the deck, and the cables all worked as one massive interconnected structure. When the deck twisted, the tower transmitted that twist directly to the deck on the other side. The tower was reinforcing the motion, not damping it. It was like holding a rope at both ends and shaking one end. The whole thing vibrates as one unit. Engineers began to experiment with breaking that connection. The first step was hinged towers, towers that were pinned at the base so they could rock slightly. Then they added expansion joints at the top where the deck rests on the tower. This allowed the deck to move independently of the tower, breaking the feedback loop. The tower could sway and the deck could twist, without each motion feeding the other. The Verrazzano Narrows Bridge in New York, completed in 1964, is a perfect example of this philosophy taken to scale. Its towers are designed to move several feet at the top, both under wind load and under thermal expansion as the steel heats up and cools down. The deck is not welded to the tower. It rests on bearings that allow horizontal movement. When the wind pushes the deck, the tower sways. And the swaying tower acts like a pendulum, dissipating energy through its own motion. The deck moves, sure, but the movement is bounded because the tower absorbs the peak loads. There is a mechanical principle at work here, and it is the same principle that makes a car's shock absorber work. When a car hits a bump, the spring compresses and stores energy. If there were no shock absorber, that energy would be released abruptly, and the car would bounce up and down for a long time. The shock absorber, a piston moving through hydraulic fluid, converts that kinetic energy into heat. It dissipates the energy. The car settles. In a bridge, the tower can play the role of the shock absorber, but only if it is free to move. If you bolt everything together into one rigid mass, there is no relative motion, no friction, no dissipation. The energy has nowhere to go except into the structural members themselves. And eventually, the repeated stress fatigues the steel, and the structure fails. The Tacoma Narrows deck failed because it had no way to get rid of the energy the wind was pumping into it. Now, here's where the story gets interesting. The phrase spin in the wind refers to a specific class of tower designs, and the most famous example is the Severn Bridge in the United Kingdom, which opened in 1966. The Severn Bridge was a radical departure from everything that came before. It crossed the River Severn between England and Wales, and the engineers, a team led by the British engineer Gilbert Roberts, decided to throw out the old playbook. Instead of a heavy truss deck, the kind that had been used to stiffen bridges since the Tacoma collapse, they used a streamlined steel box girder. The deck was shaped like an aircraft wing, a long, slender aerodynamic box. The idea was that wind flowing over this shape would produce almost no lift. It would not act like a wing at all. It would just slide through the air. But the engineers also changed the towers. The Severn towers are slender, with a tapered profile, and they are not rigidly cross-braced at the top the way traditional towers were. They are designed to bend in the wind, and that bending provides the damping that keeps the deck stable. The bridge was the first to fully integrate aerodynamic shaping with tower flexibility. The deck handles the steady wind load. The towers handle the gusts. And because the towers are allowed to move, they absorb energy from the system, preventing it from building up. The Severn Bridge was a success. It became the model for a generation of long-span bridges. But the approach has limits, and those limits became clear when engineers scaled it up. The Humber Bridge, completed in 1981, took the Severn concept and made it much bigger, with a main span of over 1,400 meters. The Humber used concrete towers instead of steel, and concrete is much heavier and more massive than steel. That mass makes the towers harder to move. They are stiff by nature. The engineers had to add tuned mass dampers inside the deck to compensate. A tuned mass damper is essentially a large weight mounted on springs and hydraulic pistons tuned to the natural frequency of the bridge. When the deck starts to oscillate, the weight moves in the opposite direction, canceling the motion. The spin in the wind tower works best when the tower is light enough to move. When you build a heavy tower, you lose that damping effect, and you have to find another way to dissipate energy. The design philosophy here is to give the structure multiple degrees of freedom, each one tuned to absorb a different frequency of wind energy. The streamlined deck handles the steady wind load. The flexible towers handle the gust loads. The bearings at the tower tops handle thermal expansion. No single element tries to resist everything. Instead, each element does its job, and the system as a whole is stable because no single part can accumulate destructive energy. This is a completely different mindset from the pre-Tacoma era. Back then, engineers tried to make every part as strong and rigid as possible. They thought of the bridge as a fortress, resisting the elements. The modern mindset is more like a martial art. You do not block the force. You redirect it, you let it flow past you, you use it against itself. The bridge moves with the wind, and because it moves, it survives. But there is a problem with this approach, and it has nothing to do with engineering. When people see a bridge tower swaying, they assume it is about to fail. They do not have the training to understand that the movement is the design working. And this is a real issue, because the movement can look alarming. The Malau Viaduct in France, which opened in 2004, is a perfect example. It is a cable-stayed bridge, not a suspension bridge, but the principle is the same. Its towers are incredibly tall, some of them reaching over 300 meters, and they visibly flex under wind. Tourists have filmed the movement and posted videos online, asking if the bridge is safe. The answer, of course, is yes. The movement is intentional. The bridge has built-in instrumentation that monitors the deflection in real time, and the engineers publish the design parameters before opening, specifically to preempt public panic. The Akashi Kaikyo Bridge in Japan, completed in 1998, is an even more dramatic case. It was under construction during the Kobe earthquake in 1995. The earthquake, which was a magnitude 6.9, struck right near the bridge site. The ground shifted so much that it stretched the bridge by almost a meter. The towers, which were still under construction, were designed to accommodate that movement. The bridge survived the earthquake, and the engineers actually used the data from the quake to adjust their calculations for the rest of the construction. The flexibility that saved the bridge from the earthquake is the same flexibility that saves it from typhoon winds, which hit Japan regularly. There is a perceptual gap here between what feels safe and what is safe. A rigid structure transmits all forces directly to its foundations. If the force exceeds the capacity of the material, the structure fails suddenly, without warning. It just snaps. A flexible structure bends, it absorbs energy, and it gives you visible warning signs. The flexible bridge is safer precisely because it moves. The challenge is that human intuition has not evolved to understand this. We see movement and we associate it with weakness. So engineers have to build the safety case into the design and communicate it clearly. Now, the spin in the wind tower solved the oscillation problem for a generation of bridges, but it is not a universal solution. It has limits, and modern bridges combine tower flexibility with active damping systems, aerodynamic shaping, and real-time monitoring. The approach is layered. The Öresund Bridge, which connects Denmark and Sweden and opened in 2000, uses a combination of flexible towers and active tuned mass dampers inside the deck. The dampers are large weights on springs and hydraulic pistons, tuned to the natural frequency of the bridge. When the deck starts to oscillate, sensors detect the motion, and the weights move in the opposite direction, canceling it out. This is a more aggressive solution than the passive tower bending of the Severn Bridge. It requires power, sensors, and computers, but it gives the engineers much more control. There is also a failure mode for overflexibility. If a tower bends too far, the main cables sag and the deck loses its shape. The Storebælt Bridge in Denmark, completed in 1998, had to be retrofitted with dampers after it was found to oscillate more than predicted in certain wind conditions. The retrofits worked, but they were expensive, and they showed that the passive approach alone is not always enough. You cannot just let the tower swing freely and hope for the best. You have to tune it, you have to constrain it, and you have to monitor it. The modern approach is a system of backups. The aerodynamic deck reduces the input. The flexible tower dissipates the energy. The active dampers handle the residual oscillations. and the monitoring system tells the operators when conditions are approaching the design limits. Each layer is a backup for the others. The spin in the wind tower is no longer the sole solution, but it remains the foundation on which the other layers are built. So the next time you cross a suspension bridge on a windy day, look at the towers. If you see them moving, you are watching the bridge doing its job. The movement is a relief. It means the bridge is absorbing the wind's energy, converting it into a gentle sway that the structure can handle. The bridge you are crossing is a living structure that dances with the wind, and the dance is what keeps you safe. The engineers who designed these bridges did not try to win the fight against the wind. They learned to lose gracefully, a little at a time, and that is why you get to the other side. The next time you feel that slight sway as you drive across a long bridge, do not grip the wheel tighter. Relax. The bridge is doing exactly what it was built to do. It is spinning in the wind, so you do not have to.